Look at some practical aspects of multi-core programming. First, it's much more fun than sequential programming. Why? Well, it's more intellectually challenging. And you have to think deeper about how to improve the performance. One of the best students I've ever had, and who also won this course competition some years ago, he said that if he had 10 seemingly good ideas about how to improve his already fast program, 9 of them would turn out to make it slower. And the reason for that is that the execution of parallel programs is so much more complex than the execution of sequential programs. And therefore it's much more difficult and requires lots of more thought to make a fast, which also means environmentally friendly program. So even though this course is about making fast programs, it can actually be seen as making programs which are good for the nature. Okay, and that's not a joke. That's really serious. Okay, more aspects to parallel programming. We are in the middle, or not middle, but we are part of the computer revolution, so that it is expected that we should be able to parallelize sequential algorithms. And since approximately the mid-1990s, industry and academia have come to a consensus of how to make easily programmable parallel machines. And it's the machines that you can buy at, it's a mobile phone, laptop or desktop or a server. They use the computer architecture of what was researched during mid-1990s. That means shared memory multiprocessors with coherent caches. Okay, so we can ask, how much do such machines cost? Well, first the price is of a very common machine or a phone. So that's well-known prices. But more expensive machines, the one that we will use in the labs, it cost initially $11,000, but we bought it used for less than 300 euros. So it was, it didn't take many minutes for myself to convince me that I should buy one for myself as well, when they had a number of such machines for sale at eBay. Okay, and it was equally easy to convince the head of the department that we must act quickly. Okay, so we did. Okay, normal prices for such a machine, slightly more powerful. Here are some examples. Well, you can read the numbers here. So they are usually quite expensive. Okay, so these machines, they are called cache coherent shared memory multiprocessors. And by shared memory means that the different CPUs can address variables in a shared or common memory. It's the same address space that the different CPUs run in. That means the programmer does not have to create messages and send to a different CPU. Okay, and cache coherent means that in some sense the caches of the different CPUs have the same content. That's a very simplified explanation, but that's what the goal is. Okay. A limitation for a shared memory multiprocessor then is that it's usually limited to one physical location. In lab 1, where we will use message passing between actors, then the actors can actually be located in different countries. So they don't have at all to be in the same physical location. Okay. Multicore is not only about cache coherent shared memory multiprocessors, but it really means a parallel computer with multiple cores. Usually that means this cache coherent shared memory multiprocessor, but not always. And how can we exploit them? Well, it's usually not about creating a new and parallel algorithm, but instead to take a sequential algorithm that seems to be easy to divide into different tasks and threads. I mean, tasks is in the general sense something to work on, and then the threads should work on the tasks. Okay. So, what can create troubles in this situation? First, Amdahl's law, that there is a limited performance improvement due to that there is not enough parallel tasks that the threads can work on. Several computer companies have gone bankrupt due to not taking this into account sufficiently seriously. Then there can be multiple threads which access the same data concurrently, and at least one of them modifies it, so we have a data race. Or we can have locks and they are waiting for each other. I mean, the threads that have taken the locks. Then we have a deadlock. Or we can have a correct program and there is enough parallelism, but we organize the computation in a way that makes it inefficient. Think of building a house. If we have 10 workers doing something in a certain it doesn't have to be building a house, of course, but that's a very good example. If we have 10 workers who build something and they have to borrow some tools from each other in too often, or have meetings too often, that's also for normal organizations, then it will not be quicker if we add 1,000 workers to build a single house. So we must organize also parallel programs in a clever way so that we can exploit the cache memories. That's really important. Okay, and why do I say that? Well, cache memories are important also for sequential programs, but they are even much more important for parallel programs, because missing, I mean, if the data is not in the cache, it takes longer time to get it, because some other thread can have it in its cache. And also different CPUs can disturb the other CPU's caches. We will come back to that. Okay. Amdahl's law. Suppose a program takes one time unit to execute, and a fraction of that, I mean between 0 and 1, can be run in parallel. Then depending on the value of p, we can be disappointed even if we add in an infinite number of CPUs. So speed up is defined as the time for the slow version divided by the time for the fast version. And with n CPUs, the speed up will be as follows. The time for the slow, that's the sequential version, it takes 1 time unit. And the time for the parallel version, it's 1 minus, I mean this is the sequential part, it's 1 minus p plus p divided by n. And if p is, I mean if we can parallelize 90% of the program, it doesn't, it's hard to get beyond, I mean it's impossible to get beyond a factor of 10 in performance improvement. And it's hard to get beyond 9, even if we have 100 CPUs. And how can computer companies go broke due to this? Well, they can invent a new exotic or not exotic hardware feature and bet that this will make their machines so much faster, not only on their own benchmarks, but on the customer's codes. And then when the customer tries their machines and they discover that there was not sufficient performance improvement, then they certainly will not buy the machine. And developing a new machine is expensive. Okay.